Welcome to Efiwe, excellence without stress.
Hi guys, we're back again on this our excellence without stress journey on this path into success, and today we're going to an awesome part in physics which is the elementary modern physics. Today we're going to study atomic models, different models by different scientists. The first one was by John Dalton that proposed that atoms were indivisible, and it was disapproved by J.J. Thomson, which believed that the atom consists of a large sphere of nucleus and then it has negatively charged inside of it, and that was also disapproved by E. Rutherford when it performed an experiment. He performed an experiment, and through that experiment, he concluded that the center of the atom consists of a large nucleus, and that the nucleus consists of majorly the mass of the atom, and around it is now the electrons surrounding it. Then we have the Niels Bohr's planetary model, which is the most accepted model, which believes that electrons are continuously revolving around the nucleus, and they can move from one excited state. This is called excited state. They can move from this point to another. Like when light is incident on this atom, we believe that this electron can move from here to this point, and it can move from this point to this point, and it can move from this point to this point. This movement is what might cause the release of energy, because if the electron drops back when it becomes de-excited, there is going to be a release of energy, and we have the Erwin Schrödinger. So the models of the atom, John Dalton is generally credited as the father of the atomic theory, but the early Greek philosophers were the originators of the concept of atom. This is an atom, this is electron, proton, and neutron at the center. They thought that matter is composed of atom and that is therefore finitely divisible, that is, it can continuously be divided. Dalton considered the atom as constituting the simplest component of matter. He viewed atom as indestructible, tiny artifacts that it can continue to be divisible. The discovery of radioactivity by Ernie Becquerel showed that atoms are complex rather than indivisible. Radioactivity showed that atoms are not indivisible or indestructible, but can disintegrate, forming atoms of different elements. The discovery of cathode rays in electric discharge tubes by William Crookes revealed that negatively charged electrons were components of the atom. In 1900, it was already established that matter consists of atoms, yes, but nothing was known about the structure of the atom. Sir J.J. Thomson, the English physicist, to propose an atomic model, he proposed an atomic model which visualized the atom as a homogeneous sphere of positive charge. That the atom, it consists of a big sphere, and the big sphere is ideally positively charged, and then there are electrons in it. He said he proposed an atomic model which visualized the atom as a homogeneous sphere of positive charge, inside of which are embedded negatively charged electrons. That was Sir J.J. Thomson's proposition, and it was also disapproved. So Rutherford model, Ernest Rutherford and his co-workers performed experiments whose results contradicted Sir J.J. Thomson's model that no, the atom is not a big sphere of positively charged nucleus, but the nucleus is at the center. So Ernest Rutherford in 1911 and his co-workers performed experiments whose results contradicted Sir J.J. Thomson's model. In this experiment, a beam of light, as you can see, the beam of light, a beam of positively charged alpha particles was directed at a thin sheet of metal foil. It was found at most that the alpha particles passed through. They passed through the foil without deflection, as if the foil were mostly empty space. Only a few of them were diverted from their path. Some of these few actually bounded backwards. They bounced backwards. The scattering of the alpha particles by the metal foil was explained as a repulsion from a heavy positively charged nucleus present at the center of the atom of the metal foil. The Rutherford proposed a planetary model of the atom, which suggested that the atom, this is the atom, consists of a positively charged heavy core called the nucleus. It consists of a positively charged heavy core called the nucleus, where most of the mass of the atom was concentrated, and around this nucleus, negatively charged electrons circle in orbit around it, around this nucleus, negatively charged electrons circle in orbits much as planets move around the sun. So this is now the Bohr's atomic model. What did Bohr say? He believes that electrons revolve around the nucleus in fixed circular orbit. He doesn't believe that it is scattered or it is just anyhow. He believes that electrons revolved around the nucleus, because we've already established that. This is it now. Let's go to our board and quickly just try to talk about what he's trying to say. He believes that this is an atom. He believes that this is an atom, and at the center, which it consists the whole mass, major of the mass of the atom, that is the real size of the atom, is at the nucleus. So this part now is the nucleus, and the nucleus is positively charged. This is the nucleus. He believes that this is the nucleus, and around it are now what? Electrons. This is what Niels Bohr was trying to propose. These are electrons moving like planets around it. So that is what he was trying to say. Look, moving like planets around. So you know the way the planets revolve around the sun. So that is the same way. That was Niels Bohr's what? Proposition, that the nucleus is at a center of the atom, and electrons is continuously revolving around it. And it's not as if they are just moving. They are moving in a quantized manner. So he said electrons revolve around the nucleus in fixed circular orbits or fixed radius and with fixed energy, not just anyhow. Again, quantization question: electrons revolve only in those circular orbits where angular momentum is equals to this value, and this n is just the shell value, it's just the shell number. Let's go to our board. It's just the shell value. So what he's just trying to say is this, that he said that the angular momentum is equals to n multiplied by h over what? Over 2 pi. So this is the angular momentum. You know what momentum is? Momentum is mass times velocity, abi? So we already know that angular momentum is the r because of the fact that it is moving in a circle, right? So this is angular momentum, r. So it's r multiplied by the what? Momentum, which is actually mvr. That is our angular momentum. So we are saying that mvr is equals to what? This n. N is just the number of the shell. H is called the Planck's constant divided by 2 pi. And this is the angular momentum of the electron. So this is it now. So this is the angular momentum of the electron that is revolving around the nucleus. So, and this n, if I have the nucleus like this, and I have different energy states 1, energy state 2. So the electrons are here. Electrons can move from here to this point. It can move from this point to this point. So this electron now, this is shell 1, shell 2, shell 3. So this place will just be 3 multiplied by the Planck constant over 2 pi. So n is just is a shell number. That is what that is trying to explain to us. So the first one we've already explained. The quantization condition: electrons revolve only in those circular orbits where angular momentum is equals to this. Then electrons can gain or lose energy, and they can change energy levels. This is what we're trying to explain here. Look at it now. The electron here can move from this energy level, can move to this point if excited. If light now is incident, on this atom, maybe they shine light, a bright light is incident on this atom, and it touches this electron will become excited. The electron is very, very stubborn. It doesn't like, it's actually revolving, but it wants to move, it wants to go. It's just like a child that is locked in a room, and wow, immediately you open the door, what will the child do? The child will rush out. So the electron that is at this point, but once light is incident on it, it can move from this energy level to this point, and it can move from this energy level to this point. And if it becomes de-excited and it falls back to the ground state, what will happen? It's going to release energy. If, for example, this energy that was coming was 4 eV, 4 electron volts, it was 4 eV, and it was incident on this electron, the electron is going to accept everything. Then it's going to move from this state, maybe this is 2, this one is 4, to this point. If it's coming back, it's going to release energy of that same size. Electron cannot stop here. It cannot stay between energy levels. It cannot stay between. It can only move from one energy level to another. And those were Bohr's theory, and it was very, very understanding. He said electrons can gain or lose energy, and they change energy levels. There is a frequency of radiation absorbed or emitted during transition is this: F is equals to change in E over the Planck's constant. So Bohr's model, idea of quantized energy state. So this is the explanation of what I've been saying. So this is the nucleus, and these are the electrons revolving. This electron can move from here to this point. You can see a photon is emitted. Why was a photon emitted? Because it was here before. This electron was at this point. Then it went from this energy level to 1. And I told you that once it becomes de-excited, it's going to release photon. Is going to release what? Photon. And that is what Niels Bohr was trying to explain. In 1913, Niels Bohr, a Danish scientist who had studied in Rutherford's laboratory, suggested a model of the hydrogen atom in which, one, the electron moves around the nucleus. The electron is revolving just like the planets is revolving around the sun. They are moving. What is the electron looking for? An opportunity to do what? To move. If it just received any form of energy, if it was here, if the electron was here, it will move from this place to this place, from this place, and once it becomes de-excited and is going back to its ground state, it's going to release energy. So they said the electron moves around the nucleus in a certain specific circular orbit, sometimes called energy levels. These are the energy levels. This is the ground state, energy level 1, energy level 2. And that the centrifugal force due to this motion counterbalances the electrostatic attraction between the electron and the nucleus. The energy of an electron in an atom cannot vary continuously, cannot just move. An electron cannot, these things are representing the circles we drew the other time. The circles I drew, like this is the ground state, then it can move to this second circle, the third circle. We just use it so we can visualize it very well. The energy of an electron in an atom cannot vary continuously, but is restricted to a limited number of districts or individual values. The energy of an electron is said to be quantized. It's quantized, that is not just anyhow. That is can only have what? Discrete values, small values. So the electrons can move from here to this point. And once the electron is falling back, at all these points of falling back, what is it releasing? It's releasing photon. Bohr thus postulated that the electrons in an atom cannot lose energy continuously, but must do so in a quantum jump. You can see the jump. It gained energy to this point, and what happened? It can come from this point back. It can come from this point back, and once it's becoming de-excited, is releasing what? Photon. So Bohr thus postulated that the electrons in an atom cannot lose energy continuously, but must do so in quantum jumps. Bohr postulated that light is emitted only when an electron jumps from one stationary state to another of lower energy level. That was what I was trying to say. Photon is only emitted, that light of photon is emitted when this electron was at this point. Maybe it was in the circle. You know that circle I drew? This circle I drew here. It was here. It was here. And it came down to the ground state. What will happen? Light will be emitted. That is what Bohr was trying to explain. He said Bohr postulated that light is emitted only when an electron jumps from one stationary state to another of lower energy. Then this is the third postulate of Bohr's model, was the angular momentum. I've explained this. He believes that electrons in an atom are quantized. That is, they are restricted to a limited number of discrete values that are integral n values. And we explained that n, that was what I explained here. When I said that the angular momentum is equals to n, which is just the number of the shell. If it is one shell, 2 shell, 3, multiplied by the Planck's constant, divided by what? 2 pi. And that is what this third postulate is talking about, where n is equals to 1, 2, 3. We can see that n is equals to 1 here, n is equals to 2 here, n is equals to 3 here. So this is the electron here. When it came to this point, and going back, maybe it became the excited photon is emitted. So then we have the electron cloud model. That was all about Niels Bohr's model. Those were the 3 postulates of Niels Bohr, and they were extremely brilliant. Because it was a breakthrough about the atom. This model visualizes the atom as consisting of a nucleus of radius 10 raised to minus 15. You know what a radius is? This is it, that the radius is 10 raised to minus 15. The electron is visualized as being in rapid motion. This is the electron being in rapid motion with relatively large region around the nucleus. So this is all these parts now is the part of the electron, and it looks like a cloud. The electron is visualized as spread out around the nucleus in a sort of electron cloud. So atomic structure and chemical behavior. So we've already agreed that an atom center, which consists of majorly the mass of the atom, is at the center, and that is called the nucleus. The nucleus is at the center, and majorly the mass of that atom is based there. So this nucleus consists of the neutron and the proton, then the electrons. I told you the electron is like the stubborn child, always moving around, always revolving, looking for an opportunity to live, looking for an opportunity to move from one energy level to another. So the nucleus consists of protons, which carry positive charge is and neutron which carry no charge. At this point, the nucleus consists of proton, P for positive, and neutron no charge, P proton positive charge. And the proton and the neutron together constitute the nucleon. That is, these two are what exists in the nucleus of an atom. Practically all the mass of an atom is concentrated in the central nucleus. That is the major mass. Only a little. The electron does not have much mass. Majorly of the mass is at the center of the atom. So the proton, neutrons, and electrons are the fundamental subatomic particles of the atom. You recollect when John Dalton was saying that the atom is the smallest indivisible part of an element, but we've noticed that it is divisible because it consists of the proton, it consists of the neutron, and what? Electron. Don't forget, the proton is positively charged, electron is negatively charged, and the neutron carries no charge. The electron is the lightest particle of an atom. It is the lightest particle with a mass of 9.1 times 10 to the minus 31, very little kg, and an electronic charge E of 1.6 times 10 to the minus 19 coulomb. The charge of the electron and the charge of the proton is the same. The only difference is that the proton is positively charged and the electron is negatively charged. But the electron is so small. Major mass of the atom is based where at the center, at the nucleus of the atom. The proton has a mass of 1.67 times 10 to the power 27. You can see how big the proton is, which is over 1,837 times heavier than the mass of the electron. You can see that 1,836 times heavier than the mass of the electron. You can see it at the center here, positively charged. It carries a positive what? Charge. That is, its charge is 1.6 times 10 to the power minus 19 coulomb, while that of the electron was what? Minus 1.6 times 10 to the power minus 19 coulomb. But the proton is heavier, 1,836 times heavier than the electron. There are the same number of protons in the atom of a given element, but different number of protons in the atom of different elements. Same element has the same number of protons, but different element has what? Different protons. Like the protons in carbon is different from the proton in nitrogen. That's basically what we're talking about. For example, there is only one proton in hydrogen atom, but 11 protons in what? Sodium atom. In a neutral atom, the number of protons equals the number of electrons. The neutron has the same mass as the proton, but it carries no charge. Don't forget, at the center, at the nucleus, is the neutron and the what? And the proton. Both of them has the same mass. They carry the same mass. That is, they are 1,836 times bigger than the mass of electron. But don't forget, the neutron has no charge. N, no charge. While the P has charge, is positively charged. We denote the atom of an element by X, and where A is the mass number and Z is its atomic number. A is the mass number and Z is its atomic number. Let's go to our board to quickly check that. A is the mass number. So if we have an element X, A is regarded as the mass number and Z is the atomic number. A is the mass number and Z is the, for example, if we have carbon 12, we have 12 and we have 6. So this 12 is the bigger mass number of the element, and 6 is the atomic number. It can also be called the proton number, the atomic or the proton number. That's what we are trying to say here. So, and we denote the atom of an element by X, where A is the mass number and Z is its atomic number. Thus, the number of neutrons in the atom of an element equals the difference between the mass number and the the atomic number. Don't forget that the number of neutrons in the atom of an element equals the difference between the mass number and the atomic number, because neutrons plus proton will give us the mass number. Neutron plus proton will give us the mass number. So if we want to know the number of protons, we're just going to deduct the mass number from the proton number. Like for carbon 12 that we saw the other time, if we want to know the neutron number now, it's just 12 minus 6, which is 6. So here, the neutron and the proton has the same value. They have the same value. That's 12 minus 6, 6, because the mass number is 12 and the proton number is what? Is 6. And don't forget, to get your neutron number, it's just the mass number minus the what? The proton number, which is what? Which is 6. So let's continue. Let's proceed. The carbon atom denoted by 12 has 6 protons and 6 neutrons. We've explained that because the neutron number is just the mass number minus the proton or the atomic number. The nitrogen atom denoted by 14 and 7. 14 is the mass number, 7 is the atomic number or the proton number, has what? 7 protons and 7 neutrons, and a mass number of 14. Since a neutral atom has the same number of electrons as the number of protons, C has 6 protons and 6 electrons. It has 6 protons and 6 electrons. So atomic number or proton number is the number of protons in the nucleus of an element. It's the number of protons in the nucleus, while the mass number or nuclear number is the total number of protons and neutrons. Don't forget that, total number of protons and neutrons in an atom of an element. The properties of the elements are periodic functions of the atomic number. So the atomic number determines their functions. When arranged in order of increasing atomic numbers, the elements with similar chemical properties recur at definite intervals, that is periodically. So in regard to the electronic structure of electronic configuration, this suggests a periodicity in the number of electrons in the outer shells of the atoms. What this is just trying to say is group 1 elements all have 1 element in their outermost shell. Group 2 elements all have 2 elements in their outermost shell, and that is evident when we draw it. Then we have the electrons in the outermost shell or shells of our atoms are called their valence electrons. They are called their valence electrons. Let's try to visualize that very quickly. I'm sure we've done this in chemistry. Let's try to quickly check this. So when we have carbon, we remember that carbon is carbon 12 and it has 6, right? So the valence electron of carbon you can see carbon is a group 4 element, and how many electrons are in the valence electron? These are called valence electrons. These are called what? Valence electrons. So it's trying to say every element in group, if we have group 1 now, like our nitrogen, all the elements, or sodium is 11 and 23. So if we draw for sodium, we know the first shell is going to take 2. The second shell is going to take 8. And the last shell is just going to take 1. So how many electrons? The valence electron is 1. Hydrogen 2 is in group 1. Hydrogen 2 has what? 1 valence electron. So that is what it's just trying to say, that the last part is always going to be what? It's going to be the same thing. They will have the same valence electrons in their last shell. And that is what we were trying to explain. And that's what we are trying to explain. So they said the electrons in the outermost shell of or shells of an atom are called their valence electrons. If the elements have the same number of valence electrons, they are grouped together. The elements falling within each group have similar chemical properties. So this is electronic configuration. So the first energy state, which is the first one, has only Is, and the second one 2s 2p. So if I want to write for the next element, is going to be 1s 2s and 2p. Next one is 1s 2s 2p 3s. Then we'll come to 1s 2s 2p 3s 3p 4s, and so on and so go. 1 2s 2p, we're going to go to the 3s, we're going to go to 4s 3p, 5s 4p 3d, 6s 5p 4p, and so on and so forth. And this is how you write. So shells, S shell is 2 electrons, P shell 6 electrons, D shell 10 electrons, and F shell 14 electrons. This is electronic configuration. And we have the periodic table. This was what we were trying to say. This is group 1. All the elements in group 1, they have 1 in their valence electrons. Group 2, and so on and so forth. Group 8, you know, these ones are stable electrons. They don't have anything. They don't have any excited electrons. They are balanced. Isotopes. What are isotopes? Isotopes are atoms of the same element which have the same atomic number but different mass number. They have the same atomic number but different mass number. Look at this chlorine. Chlorine here now, we have chlorine 35, and chlorine 37. Can you imagine? So we have this one as 35, we have this one as what, 37. So this is isotopes. Isotopes are those atoms with the same number of proton. We've already established our proton or atomic number, but different what, mass number. So look at this now, it has 17 protons, right? But if you want to check, protons and electrons are going to be the same, but the neutron will be the difference, because neutron is 35 minus 17, that is the mass number minus the minus the proton number. So 35 minus 17 will give me 18. 35 minus 17 will give me what? 20. Yeah, and those are isotopes. Same atomic number, but different mass numbers, isotopes. So this is protium, deuterium, and what? Tritium. So look at this one was 1, 2, and 3. They all have the same atomic numbers, but different what? Mass numbers. These are isotopes of hydrogen. Then we are going to radioactivity. Radioactivity, another important topic. So the phenomenon of radioactivity was discovered in 1896 by a French physicist, Henri Becquerel. He noted while performing some experiments that uranium gave out some kind of rays that would penetrate through thick black paper and affect a photographic plate placed on the other side. This phenomenon is called radioactivity, and substances that give rise to radioactivity are called radioactive substance or element. They are called radioactive substance or element. So radioactivity is a spontaneous decay or integration of the nucleus of an atom, of the atom of an element, during which it emits either the alpha and particles, or emits either the alpha, beta, or gamma part rays, or a combination of any or all of the three. Sorry, that was a mistake. It should be alpha, beta, and gamma, or the three of them. So radioactive elements are those elements that emits radiation from their nucleus, either radium, thorium, radon, ionium, or polonium. So those are radioactive elements. So the phenomenon is called radioactivity. That is the spontaneous decay or integration of the nucleus of the atom of an element, during which it emits either the alpha, the beta, or the gamma rays. Types of radiation from radioactive elements. The experimental genius of the British physicist Ernest Rutherford unraveled the nature of the radiations emitted by radioactive elements. He and his co-workers discovered that the emissions were penetrating and were of 3 different types. In their experiments, they placed a small sample of radium at the bottom of a small hole drilled in a block of a lead. You can see it now. This is the radioactive material. This is the lead block, a radioactive plate, and this is, you see that this one now, it emitted what? Alpha, it emitted beta here, and it emitted what? Gamma ray. So he said he and his co-worker discovered that the emissions were penetrating and were of 3 different types. In their experiments, they placed a small sample of radium at the bottom of a small hole. You can see it at the bottom of a small hole drilled in a block of lead. The radiation emitted from this radium emerged from the hole in a narrow beam. The rays were subjected to a strong magnetic field placed at the side of the film. A photographic plate situated at appropriate side. You can see the photographic plate to receive the rays showed that the parts of some rays were bent to the right, some to the left, and some went straight. You can see it unbent. You can see the gamma straight. The alpha went this way, the beta and the gamma went straight. And that was an awesome experiment. Types of radiation. Electrically charged plates placed at the side of the beam, as shown, gave the same effect. Thus, one of the 3 types of radiation was deflected in a direction, showing it consists of positively charged particles. They were bent towards the negative electric plates. You understand that? Because don't forget what we said, that like charges attract, like charges repel, while unlike charges attract. So this ray that went towards the negative indicates that it is positively charged. Indicates that it's positive. They were bent towards the negative electric plates, or the south pole of the magnetic field. These were called alpha particles. And they were bent towards the negative. It means they are what? Positively charged. Another type of radiation was deflected towards the positive electric plate, or the north pole of the magnetic field. This shows them to be what? Negatively charged. They were called the beta particles, because they went to the positive part of the plate. Then the third type type of radiation that was neither affected by the electric or magnetic field indicated they were not charged. They were actually electromagnetic radiation and are called the gamma rays. They were not moved either by positive side or the negative side. Look at it. Look at it from this picture. The gamma ray was going straight. This one, alpha, moved towards the negative. The beta moved towards, you can see the positive plate here, and we can see the negative plate here. The alpha, which is positively charged, went to the positive side of the plate. The beta, which was negatively charged, came to the positive side, but the gamma went straight because it had no charge. It had no charge. It had no charge. So this is it. So this was what we're talking about. The X-rays, they have the helium nucleus. Helium, that is, the mass number is 4 and the proton number is what? 2. So the helium nucleus consisting of 2 protons and 2 neutrons. Don't forget that the proton and the neutrons add up to give us our what? Mass number. And that's why we have the mass number here as what? As 4. We have the mass number as 4. So here they are electrons, because you know the electrons are negatively charged now. So basic elementary particles in all atoms. Then this one, they are electromagnetic waves consisting of photons, lights. That's why they call them electromagnetic rays. So we have the charge. This one was positively charged. You can remember that because it was deflected towards the negative plate and it carries 2e. And you know that E is 1.6 times 10 raised power minus 19. So it's twice of it. While this is negatively charged, which is minus E, and that's 1.6 times 10 raised power minus 19. Then we have the neutral particles, no charge at all. So this one is 100 times greater than beta rays and 10,000 times greater than the what? Gamma rays, ionizing power. Alpha has higher ionizing, they have 100 times ionizing power than the beta rays and 10,000 ionizing power than the what? Gamma rays. While the beta rays ionizing power is comparatively low, and the gamma rays, it has very less ionizing power. They have very less ionizing. Why? Because they are not charged. They are not charged. Have very light ionizing power. This one's one is very low. Then penetrating power. That is where the gamma ray come. This one has very low penetrating power, like it can only go through a sheet of paper. This one's penetrating power is more than that of the X-ray. So penetrating power is greater than that of a ray, of the alpha ray. They can penetrate through a thin metal foil, but this one, they have high penetrating power, greater than that of the beta ray, and they can penetrate through thick metal blocks, through very thick metal rock. So gamma rays have high penetrating power. So effect of electric and magnetic field. These ones are deflected by both the field in accordance with Fleming's left-hand rule. These ones are also deflected by both the fields, but the direction of deflection is opposite to that of the alpha rays in accordance with the Fleming's rule. We understand deflection. This one went towards the negative plate because it's positively charged. This one came towards the negative charge because it is positively This one went towards the positive plate because it is negatively charged. Then they are not deflected by both the fields. They are not deflected by either the electric or the magnetic field. Their speed ranges from 1/10 to 1/20 times the speed of light, while their speed can go up to 9/10 times the speed of light. They travel with the speed of light. Fast, 3 times 10 raised by 8 meters per second. They travel with the speed of light. Radioactive constant and decay or half-life, decay constant. So half-life now of a radioactive element. We already talked about radioactivity, Abi. So it's just the spontaneous decay of an element, spontaneous decay of the nucleus of an element. So half-life of a radioactive element is the time taken for half of the atoms initially present to in the element to decay. Half-life. So half-life, this is the element, the time it takes it to decay. That is what is called the half-life. That is what is called the half-life, the time for it to decay. If the half-life of an element is T years, it means that after 7 years, 1 gram of the element will have a mass of 1/2 gm. After 2 years, the mass of the element will be 1/4 of that mass. So since the mass is 1, in 2 years, it will be half of it. If 1 gram of the element will have mass of 1/2 gm, after 2 years, the mass of the element is just dividing it by 2 in multiples of 2. Thus, if you have 1,000 atoms of a radioactive element initially, whose half-life is 10 years, then every 10 years, it will be dividing by half. So in 10 years, it will have 500. In 20 years, 250. In 30 years, 125. As simple as that. That is what is called the half-life. Once you know the half-life of an atom, then you know that, okay, in this amount of years, it's going to divide by 2. Half-life of a radioactive element is the time taken for half of the atom initially present in the element to do what? To decay. So look at this atom. It was 1000, and they told us the half-life is 10 years. Let's go to our board. Let's go to our board to check this. So look at it now. The element was what? 1000. 1000. And they said the half-life. We already know what half-life is. The half-life was what? 10 years. Right? Then it means that every 10 years, half of this will be decayed. So we have it now. This was the total. We have the mass now was 10,000. 1000. So in 10 years, it will be what? 1000 divided by 2, which will be equals to what? 500. So in 20 years, what will it be? It will be 500 again, because that's what is left, divided by 2, which will be equals to what? 250. Again, in another 30 years, what will happen? 250 divided by what? By 250 divided by what? 2 again, and so on and so forth. And that is what is called the half-life of a radioactive element. That's called the half-life of a radioactive element. Then we have what is called the decay constant. The rate of decay, when you say rate, it's talking about time. The rate of decay of radioactive elements is found to be proportional to the number of atoms of the material present. So the rate of decay, have you seen it? The rate of decay is proportional to the number of atoms of the material present. So supposing there are n atoms of a radioactive element, there are n atoms present at a time z, this is the time, then the probable number of disintegration per unit time or activity can be expressed by change in n divided by change in t. The minus just signifies that, okay, this thing is what? Is decreasing. It's decreasing. So this, you know that when you have a proportionality sign, we've already accepted that. Then there's going to be, when we change it, then we're going to have a constant. And this is a constant called the decay constant. Decay constant. So where lambda is the decay constant of the proportionality called decay constant. Decay constant is defined as the instantaneous rate of decay per unit atom or substance, or you can call it the number of atoms disintegrating per second divided by number of atoms in the source at that time. So this one is related to the time. The number of atoms I want to disintegrate divided by its time divided by the number of atoms at that time. So this is a question that we can quickly solve. So we have a radioactive element and it has an half-life, right? And we already explained what half-life is. Half-life is the time for that element to divide into 2. Half-life, it has an half-life of 10 years. We don't know the size of the, but we said a certain radioactive element has a half-life of 10 years. How long will it take to lose 7/8 of its atom? It has a half-life of 10 years. So we can just assume, because it did not give us the size of the atom, it did not give us this thing, but they said it has a half-life of 10 years. How long will it take to lose 7/8 of its atom? Don't forget, the whole atom is going to be what? 1, because it's a fraction. Sorry, let's go back to our example. Wow. Oh God. I'm coming. I'm trying to open the board. The board is seizing a bit. We don't know why it's doing that. Sorry about that. Okay. Okay, let's just continue explaining. So what we are saying here is this element has a half-life of 10 years, right? We already know that the half-life is the time it takes to do what? To disintegrate. It's the time it takes to divide to half of it, half of what it was. So now, how long will it take to lose 7/8 of its atom? How long will it take to lose 7/8? And we know that if we are looking for 7/8, how many atoms will be left? 1/4. So let's check our solution. If 7/8 of its atom has been lost, so what is happening? 1/8 remains, right? 1/8 remains. So half-life is equal to 10 years. So if n, let's assume that the atom is n, we have n atoms presently, half of it in 10 years will be what? n over 2, right? In 20 years, n over 4. Then in what? In 30 years, we're going to have what? N, because it's a multiple of 2. 2 times 2, 4. 4 times 2, 8. The next one will be 8 times 2, 16. 16 times 2, 32. Are we getting that? So this is it now. So atoms that will remain is going to be n over 8 will remain afterwards 30 years. N over 8 of the atom. So therefore, it takes 30 years to lose 7 over 8 of its atom. Let's explain that again. We said a certain radioactive element has a half-life. This is because our board is not okay. Guess we're having it back. Okay, so we have the elements here. We said we have a certain radioactive element. We don't know the size, but let's just assume that the radioactive element is N. Let's assume it's N. They are not asking us that how long will it take for 7 over 8 of it to disintegrate? And we already know that, and they said the half-life is what? The half-life is how many years? The half-life is 10 years. They're not asking that how long will it take for 7 over 8 of its atom to disintegrate. So we already know that we have N atoms, right? We have N atoms. So we are looking for how long. And don't forget half-life. The half-life is 10 years. So in N over 2, we disintegrate in what? In 10 years, right? And I thought it's a multiple of 2. Then the next one will be what? N over 4. N over 4 in how many years? 20 years. Then the last one will be what? N over 8. Because it's 2 times 2, 4. 4 times 2, 8. The next one will be 32. That will be what? In 30, what? In 30 years. So that is the amount of years that it will take. So it will take what? 30 years for what? 7 over 8 of the atom to what? To disintegrate. To take 30 years. So that is what we have here. It will take what? 30 years for 7 over 8 of its atom to what? To remain unchanged. For to disintegrate, or for it to lose 7 over 8 of its atom. The next question said, how long will it take until 1 over 4 of the atom originally present remain unchanged? We've already done that. 1 over 4 now. So what will that be? So it takes what? 30 years. Okay, we have N over 2 atoms remain after 10 years. How many will remain after 20 years? N over 4, because we don't know what the N is. And they're asking us that, how long will it take for only 1 over 4 of the atom? And we know that N is the total atom. So that is just N over 4 of the atom. So N over 4 atoms remain what? After 20 years, just as we've explained on our board. N over 2 in 10 years. Then over 4 is what? 20 years. N over 4 is 20 years. So it will take 20 years for 1 over 4 of the atom original present to remain what? Unchanged. To remain unchanged. Natural radioactivity. When a radioactive element undergoes radioactive decay, it may emit either a alpha, beta, or gamma ray. This changes the atomic number of the element. Hence, a new element is what is formed. It changes the atomic element, so a new element is formed. For example, radium-226. We can see this radium now. The mass number is 226, and the atomic number is what? Is 88. When it was bombarded, so okay, for example, radium-226 decays by emitting an alpha ray. So look at it now, it decays by emitting what? An alpha ray. It decays by emitting an alpha particle to turn into a new element, radon. Look at it now, radon, which is 222 and 86, and that is it now. An atom, before John Dalton said an atom is indivisible. Can you see what this atom has done? It has splitted to another atom. It has splitted into an atom by disintegrating. So, and it emitted what? The alpha particle. Don't forget, the alpha particle has what? The mass number 4 and proton number 2. So, for example, radium-236 decays by emitting an alpha particle to turn into a new element, radon. So, radium-226 has a mass number of 226 and atomic number 228, and hence it is denoted by what? Ra. And look at it now. You know that this is the alpha particle, which is positively charged. So if this is deducted from this, we're going to have 222. If this is deducted from this, we're going to have 86. Addition of these two is going to give us our radium 226 back. But what has happened? The radium has disintegrated to form another element, something that John Dalton said it wasn't possible. So this radioactivity has totally disapproved John Dalton's model about the atom, because this radium now has disintegrated into another atom, by releasing the alpha particle plus energy. You know that energy must always be released. Artificial radioactivity. If the radioactivity is induced in an element, with either the alpha or beta part, for example neutrons, the process is known as artificial radioactivity. If the radioactivity is induced in an element by irradiation, for example neutrons, the process is known as artificial radioactivity. By irradiation, we mean exposure to radiation either by accident or by intent. That is, if we expose an element to radiation and it emits either the alpha or the beta particle, then we call it an artificial radioactivity. That is, it's not spontaneous, it's not natural. An ordinary material, not normally radioactive, is made radioactive by bombarding it with radioactive particles. Look at this now. By bombarding it with radioactive particles, we bombarded nitrogen with alpha particle. And what did it do? Look at it now. It became fluorine 18, it became fluorine 18. Are we clear with that now? And that is what we are trying to say. And look at it, it emitted hydrogen and oxygen, and an isotope of oxygen plus energy. And this part is called the artificial radioactivity. You can see that we bombarded these elements with helium, which is an alpha particle. And what happened? It became fluorine. Again, it became oxygen, and again it became hydrogen, because addition of these two will give us our fluorine. Back. Radioisotope. Isotopes can be made artificially by bombarding the neutrons or protons or deuterons of the element. E.g., this was bombarded, and look at what it released. It released another element plus energy. It released another element plus energy. Such artificially produced isotopes are unstable and decay with the emission of alpha particles, beta particles, and gamma rays. They are therefore called radioisotopes. That is, we are creating another isotope of an element by bombarding it with either the alpha, the beta, or rays. By bombarding with either the alpha or the beta rays. So radioisotopes or radioactive isotopes are isotopes that are made artificially by bombarding neutrons or protons or deuterons as elements. The uses of isotopes. Radioisotopes are used in medicine as radiotherapy, industry to study defects in metals and welded joints, agriculture as radioactive tracers and preservatives, and in geology research for radio dating. That's the importance of radioisotopes. Then what are the health hazards of radioisotopes? So when the body is exposed to radioactive substance for a long time, the radiations penetrate the body and can destroy cells in tissues and upset natural chemical reactions. Such radiations can bring about genetic changes or mutations, causing cancer and undesirable hereditary effects. So it's not good to be exposed to radioactive substances. Radiation from radioactive substances can kill a person, cause sterility, and cause blood abnormalities. Because of this effect, workers in radiological laboratories must monitor their radiation exposure. They should be shielded with thick blocks of lead or iron or concrete. Application of radioactivity. It can be applied in agriculture and scientific research. Radioactive elements are used in agriculture as radioactive tracers and to induce mutations in plants and animals to obtain new and improved varieties. Geologists and ecologists use the measurement of half-life to estimate the age of rocks and carbon-4 dating to date the recessed organic remains. This is called radioactive dating. Medical field, gamma rays. Gamma rays from radioactive substances are used to treat cancer patients, to sterilize surgical equipment, food, etc. In industry, radioactive elements are used in industry to study the defects in metals and welded joints and check metal fatigue. Those are the applications of radioactivity. Nuclear energy. The protons and neutrons in the nucleus of each atom are held together by powerful nuclear forces. An enormous amount of energy is therefore required to tear the nucleon apart. A serious amount of energy is needed to be able to tear the nucleon apart. Nuclear fission, as was shown in 1934 by Enrico Fermi, the heavy nucleus of uranium-235 can be split. The nucleus, we already said that for us to split the nucleus we need serious energy. So they said the heavy nucleus of uranium-235 can be split into two other elements, krypton and barium. This is krypton and this is what barium. It can be split into krypton, this is barium, and this is krypton, by bombarding it with a slow neutron. You can see it now. We bombarded this uranium by neutron and it gave us barium, it gave us krypton and what? Barium and krypton. And there must always be the release of energy. It was found that the total mass of the component product is less than the mass of the original uranium. It was found that the total mass, look at it, of the component product, that is when we add it together, it was lesser than the mass of the original uranium. The difference in mass is a measure of the nuclear energy release. The difference in mass is because of the energy release. So, and don't forget, E is equals to mc squared, where E is the energy release and m is the mass, difference in mass, and c is the velocity of light. So what is nuclear fission? Nuclear fission is the splitting up of the nucleus of a heavy element into two approximate equal parts with the release of a huge amount of energy and neutrons. That is fission. Fission is breaking down of a huge element, of the nucleus of a heavy element. Nucleus of the element, don't forget that the mass of an atom is basically at the nucleus. So breaking the nucleus is done by is called nuclear fission. Nuclear fission is the splitting up of the nucleus of a heavy element into two approximate equal parts with the release of huge, you can see the huge amount of energy. We bombarded uranium with what? We bombarded uranium with what? With this neutron. And what happened? It created new elements. Nuclear fission. Fission then is just the opposite. Fission is nuclear process in which two or more light nuclei combine or fuse to form heavier nuclei with the release of a large amount of energy. There is always release of energy. We can say hydrogen, two isotopes of hydrogen coming together to form what? Helium. And there is what? The release of energy. So we have the deuterium, we have the tritium, we have the helium, and we have the neutron. So look at it. Fusion is a nuclear process in which two or more light nuclei combine or fuse to form a heavy nucleus with the release of a large amount of energy. A typical example of nuclear fission is the fission of two hydrogen nuclei to form the helium. And that's what we've seen here. Advantages of fusion over fission. Fusion is more easily achieved with lightest elements such as hydrogen. Nuclear repulsion is easily overcome as nuclei approach each other. The raw material required for fission are more cheap and readily available. For example, hydrogen can be obtained by the electrolysis of seawater, which is cheap and in plentiful supply. Fusion process processes are less dangerous. Its radioactive byproducts. There is no upper limit to mass of the hydrogen that can be exploded in the nuclear fission process. So very large energies can be obtained. Nuclear fission has been used in the hydrogen bomb. So this is nuclear fission, and this is nuclear fission. A big one will split. Then nuclear fission is combining small ones to form a big peaceful uses of nuclear energy. Many nuclear power plants are now being used to generate cheap electricity for countries which lack oil or coal. Nuclear power stations have become the ultimate solution to the problem of energy. In the medical field, several fission products obtained in nuclear reactors are used for radiotherapy. Radioisotopes from nuclear plants are used in agriculture as radioactive tracers and preservatives, and some spacecraft, ships, and submarines are powered by nuclear energy, such as vehicles have built-in reactors. Energy quantization. What is energy quantization? Some of the important postulates of the Bohr's model of the atom was that electrons move around the nucleus in specified orbits. I explained that. In these orbits, they can move without radiating energy. They can move from here to there without radiating energy. They can require or lose energy only in discrete units called the quanta. Bohr suggested that electrons in an atom exist in districts quantized energy states. Quantized energy. You know, I explained this, that the electrons can move from this ground state to this point, and if it is going back to the ground state, what will it release? It's going to release photon. It's going to release photon. So the Bohr's model and quantized energy. Look at this electron, excited, happy. It actually electrons revolve around the nucleus just like planets revolves around the earth. Then when there is what's it called, light touching it, what will happen? It becomes excited and leaves the ground state. You can see it now, low energy orbit, which is called the ground state, and become excited and come to this place. So energies are quantized. In other words, the energies are limited to discrete what values. They are quantized, limits to small values. So look at it being excited. When light is incident on this atom, then it becomes excited, leaves that point and go to another energy state, and that is what Bohr's model proposed. Energy quantization. In 1902, Max Planck was able to show that experimental observation in the radiation emitted by substances could be explained on the basis that the energy from such body is emitted in separate or discrete packets of energy known as energy quanta, and the value is HF. E is equals to HF, where F is the frequency of the radiation and H is a constant known as the Planck's constant. Energy quantization. Thus, the energy E of one quantum of radiation or photon is given by E is equals to HF. This is known as Planck's theory of radiation. This is just explaining what the electron does in this place. The term quantum means fixed amount or discrete or separate amount, or as distinguished from a continuous quantity. Planck's quantum hypothesis does suggest that the energy of radiation can be E is equals to HF or 2HF or 3HF, where 2HF is just N is equals to 1, N is equals to 2, or N is equals to 3. But there cannot be vibrations or radiations whose energy lies between these values. That is, we cannot have N and half. We cannot have 1 and a half. We cannot have the electrons moving to this point or moving to this point. The electron can either move from here to this point or to this point. We cannot have the electron at the center. That's what that statement is saying, that Planck's quantum hypothesis does suggest that the energy of radiation can be E equals to HF or 2HF. That is when N is equals to 2, or 3HF when N is equals to 3. But there cannot be vibrations or radiations whose energy lies between this value. We cannot have it here, 1.5 or 2.5. That is, energy radiated is not a continuous quantity, but is rather quantized. It exists only in discrete amounts. This is the meaning of the concept of energy quantization. Atomic energy levels. Electrons in atoms are believed to be arranged around their nucleus. We've explained this, we've established this with all what we'll be explaining in and around their nucleus in positions known as energy level or electron orbits or electron shells. Each electron in a given atom possesses a specified amount of energy that is related to the distance between the electron and the nucleus, related to the distance between the electrons and the what? And the nucleus. Electrons in the orbit closest to the nucleus have the highest energy. That is, it takes more energy to remove such electrons from the first energy level than to remove electrons from any of the other higher levels. Such electrons in the closest orbits to the nucleus are said to be in the ground state or in the lowest energy state. That is, they are at rest. And it's so difficult for us to just displace them. It's just like when we talk about the sodium. When we're talking about the sodium, you know, we said we have 2 here, we have 8 electrons here, and the last one we have 1. For us to displace this last electron is easier than to displace the one that is close to the nucleus of the atom. These ones at the ground state have more energy than the ones that are here. These ones are easily displaceable. That's what that statement was trying to explain to us. Said electrons in the orbit closest to the nucleus have the highest energy. That is, it takes more energy to remove such electrons from the first energy level than to remove electrons from any of the other energy levels. Such electrons in the closest orbits to the nucleus are said to be in the ground state or lowest energy level. So the energy of an electron is given by this. Is how to solve the energy of this energy of an electron, where N is the electron's quantum number and R is a constant. The minus sign signifies that one must do work on the electrons to remove it from the atom. You must do work to take the electron from its atom. Atomic energy levels. It is customary to draw horizontal lines to represent energy levels. This is the ground state, this is the next state, just as I drew the circle, but we're just trying to represent so we can visualize it. It is customary to draw horizontal lines to represent energy levels. This is called energy level diagram. Energy states or levels are numbered n. So this is n equals to 1, 2, and 3, starting from the what ground state as n equals to 1. When electron is infinitely far from the atom or is completely removed from the atom is said to be ionized. It's said to be ionized. You know, when we have NaCl, let me clean the board. Remember when we have Na, you know, Na is 11, 23, that's sodium, and we have chlorine 17 and 35. You know, when we want to draw them, when there is a combination between them, Na is the first circle is going to have 2, next energy state is going to have 8, 1, 2, 3, 4, 5, 6, 7, 8. Then we have for chlorine now. Chlorine is 17, 1, 2. Okay, sorry, the first one is going to have just 2. The next one is going to have 8, 1, 2, 3, 4, 5, 6, then 7, 8. Then the last one is going to have 7 to make it 17. So this is the amount of electrons that's revolving around the nucleus. 1, 2, 3, 4, 5, 6, then 7. So we know that this, there can be, okay, I've not drawn the last one of this sodium, which is 1. So this electron now, once it leaves and joins with this one, we believe that that's ionization of the electron. Said when an atom is heated or bombarded with an energetic particle, its energy is increased and it is said to be excited. When an electron is infinitely far from the atom or is completely removed from the atom is said to be ionized. It's said to be ionized. What happens then when electron leaves and joins with this one, and this becomes a compound? Na releases its electron and gives it to chlorine so that they can have a stable octet structure. At that point, we say that it is what? It is ionized. It is ionized. It said when an electron is infinitely far from the atom, I know that the energy level will be very, very small. When it is infinitely far from here, this is the point, or is completely removed from the atom is said to be ionized. The energy of this state with N is defined as 0. It's defined as 0. When an atom is heated or bombarded with an energetic particle like light, maybe the electron was at this point and light is incident on it, it will become so excited. As excited is like a stubborn child that wants to leave the house. It will become so excited and goes to the next energy level. But when it becomes the excited, what happens? It comes back to the ground state, and what will be released? Energy will be released. So when an atom is heated or bombarded with an energetic particle, its energy is increased and it is said to be excited. Yes, I've explained. It will be happy. It will now leave where it was and go to another energy level. It cannot stay between this point or this point. It can only move from here to here or here or here. During excitation, that is the process of increasing the energy level. Yes, it was here and it moved to another energy level. That is the process of increasing the energy of the atom. One or more of the atomic electrons may move to a higher energy level. Yes, they might move. It can move from here to this point. And when it becomes de-excited and comes down back, what does it do? It releases photon. So the electron possesses this higher energy as long as it remains in that excited state. But once it comes back to the ground state, what happens? It releases its energy. If the electron was here and comes back to this place, it's going to release the energy that is between this stage and this stage. Atomic energy level. Because excited states are unstable, the electron soon jumps back to its original orbit or energy and emits a photon or quantum of light with a characteristic frequency f and wavelength lambda. So E is the energy in the excited state and H is the energy in the ground state. E is the energy in the excited state and H is the energy in the ground state. Atomic energy levels. Electrons can also jump from one allowed higher energy level to a lower allowed energy level. The energy of each radiated photon is therefore proportional to the length of its corresponding atom. So this is an example. It said an electron jumps from one energy level to another in an atom, radiating 4.5 times 10 raised to the power minus 19 joules. If the Planck constant is this, what is the wavelength of the radiation? Take velocity of light to be equal to. So we have an electron which was at in the ground state. Then what happened? Maybe light was incident on it, and what happened? It jumped to another energy level, and now we are now asked to get the wavelength. There is a relationship. Don't forget the energy at the excited state minus the one at the ground state is equals to what? HF, where F is the Planck constant and F is equals to the what? F is the frequency. F is the frequency. And don't forget the relationship between frequency and this thing, frequency and the wavelength, frequency, wavelength, and the speed of light. So let's go to our board. So don't forget we have E, which is the energy, which is equals to HF, and don't forget F, which is the frequency. C is equals to what? F lambda, right? Then what is our lambda? Our lambda can also be equals to what? C over F, right? Our lambda can also be equals to C over F, because we are looking for our lambda. So this one is E is equals to what? H, right, which is a constant, then multiplied by what? C over F, because we don't have our lambda. So we can represent our lambda. No, sorry, we are looking for our lambda, so let's put it there. So let's use lambda as the sort of formula rather. So lambda will be equals to what? Lambda will be equals to C over what? F. Yes, lambda will be equals to C over F. Lambda will be equals to C over F, or F lambda. So let's go. So we have it here now that our our F is equals to C over lambda. Our F is equals to C over lambda. So we can put that, okay, we are representing the F, rather, sorry. We have E is equals to H over F. So our F is equals to what? C over lambda. So we can put it there now. So our E can also be equals to H C over what? Over lambda. Can also be equals to H C over lambda. So what is our energy? What energy were we giving? We're giving the energy, Abi. We have E, which is also equals to the energy at the ground state minus the energy at the excited state is also equals to what? HC over what? Over lambda. We understand that this is the electron. This was the electron. This is the nucleus, right? Let's assume that this is the nucleus which contains the mass. Then the electron was here. Then light was incident on it. Light came. It's just as if you opened the door to a stubborn child. Then you know what happened? It became excited. Then the energy changes from here to here. So we have to subtract it. The energy level here minus the energy level here is what we're going to have to subtract. And that's what we were trying to do. Let's check what we were given. So we have it here. So an electron jumps from one energy level to another. An atom radiating, this was the energy that it had. So if Planck's constant is this, what is the wavelength of this? So we have the energy to be this is equals to 6.6 of F. And don't forget what our F was. Let me write our values out. Let me write our values out. So we have that. The Planck's constant, we have the Planck's constant at 6.6 times 10 to the power minus 34. And we have what? We have our speed of light to be 3 times 10 to the power 8. And we have the energy to be this. So let's go back to our board to see what we are doing. So look at it now. We already have this. So the value of our energy, which was what? Let's go back, and our energy is 4.5 times 10 to the power minus 19. So 4.5 times 10 raised to the power minus 19 was our energy, is equals to this. We're not giving the difference in the energies. So we have our Planck's constant, and we have our speed of light, and we are looking for our lambda. So we're going to make lambda as a formula. Our Planck's constant is 6.6 times 10 raised to the power minus 34. 6.6, so that will be equals to 6.6 times 10 raised to the power minus 34 multiplied by the speed of light, which is 3 times 10 raised to the power 8, right? Divided by the lambda. So now we are looking for our lambda. So what will our lambda be? Our lambda then will be equals to what? 6.6 times 10 raised to the power minus 34 multiplied by 3 times 10 raised to the power 8 divided by what? 4.5 times 10 raised to the power minus 19. And then we're going to get the wavelength. And so that is it. That is the wavelength. So look at it now. This is an electron. We've already drawn the electron. It was excited and it moved from one energy level to another. Normally, we're supposed to subtract the energy levels to get our HF. This is equal to this. And we know what our F is. Our F is equal to C over lambda. So putting this into the equation, we were able to get what our lambda was. We were able to get what our lambda was. Frank Hertz's experiment. Experiments performed by Frank and Hertz gave one of the most direct proofs of the existence of energy levels or electron shells within an atom. Energy levels. In this experiment, it was possible to measure the energy necessary to raise an electron from the ground state in an atom to an outer orbit or higher state, or to remove it from the atom entirely. Through this experiment, we were able to measure the amount of energy that we can put on an electron from it and take it from its ground state to another energy level, or to even remove it totally from the atom. They bombarded atoms in form of mercury or sodium vapor with electrons emitted from a hot filament and accelerated to a higher energy, several electron volts. That was the experiment. Atomic spectra, color and light frequency. When the gas atoms are excited, look at it. This is oxygen absorption, carbon absorption, hydrogen emission, and hydrogen. When the gas atoms are excited, they give off light. Yes, I already explained that. They give off light, which when analyzed is seen to consist of light of one wavelength or color. The type of spectrum is called a line spectrum, or the spectrum of the elements. Spectral lines. You can see the lines, spectral lines. A line spectrum is a spectrum that consists of a number of well-defined lines, each having a particular frequency or wavelength of color. A continuous spectrum, on the other hand, consists of light of all colors or wavelengths. The electron in an atom can only have energy corresponding to the set of electron energy levels in the atom. When the atom is supplied with energy or it is excited, an electron is raised from a low energy level to a higher one. We've explained this countless times. And don't forget, E2 minus E1 will give us our HF. That is the state it was before to the state it is. You subtract it, where H is the Planck's constant. The photoelectric effect. When light falls on metal surface, when light falls on a metal surface, what happens? This is the light ray coming, came to a metal surface. Electrons are what? Emitted. Electrons is always looking for every opportunity to leave. Electrons are stubborn. They are energetic. They are not like the proton and the neutron that are always staying jeje. Electrons are always about moving. So when light falls on a metal surface, electrons are emitted. This is photoelectric effect. The emitted electrons are known as photoelectrons. A positive feature of this phenomenon was first discovered by Leonard in 1902, which and that was the maximum kinetic energy of the emitted electrons, and that the maximum kinetic energy of the electrons was independent on the intensity. That the energy of this electron is not dependent on the intensity of the light. When I put big light, that is when the electrons will leave more, or when I put small light, it's telling us that no, the maximum kinetic energy, kinetic energy is the energy a body possesses by virtue of its motion. It's telling us that the maximum kinetic energy of the emitted electrons was independent of the intensity of the incident light, but was proportional to its frequency or the wavelength. So it means that how fast the electron is going to leave is not dependent on the type of light. Maybe, let me use a big light, but it is dependent on the frequency or the wavelength. So what are photocells? Photocells are used in burglar alarms, television cameras, automatic doors, automatic street lights, and automatic digital counters. So these are the importance of photocells. Einstein's equation and explanation. In 1909, Einstein proposed an explanation of the photoelectric effect using a concept first put forward by Max Planck, that light wave consists of tiny bundles of packets of energy known as photons or quanta. Each photon or light or electromagnetic wave has an energy HF, where that H is the Planck's constant, and this is the value, and F is the frequency of light, and F is the frequency of light. S's idea can be expressed in an equation as HF is equals to W, which is the work function, plus half mv squared. You know that half mv squared is the what? Kinetic energy. So HF is equated to be W plus half mv squared. The threshold frequency is the frequency of the light, which which falling on the surface is just sufficient to liberate electrons without giving them any additional kinetic energy. That is the threshold frequency. So this is the threshold frequency point here. So the threshold frequency is the frequency of light, which falling on a surface is sufficient to liberate the electrons, just to liberate them without giving them any addition. It's not giving them, making them faster, but it's just what, allowing them to be able to live where they are. That is what the threshold frequency. So the threshold frequency is the frequency of light, which when falling on a surface is just enough to liberate the electrons and is not adding to their what, kinetic energy. The work function for W of a metal is the minimum energy required to liberate an electron from a metal surface. Have you seen the difference? Threshold frequency is the frequency of light, which falling on a surface is just sufficient to liberate electrons without giving them any additional kinetic energy, while the work function of a metal is the minimum energy required to just liberate the electron from the metal surface. So X-rays. X-rays was discovered accidentally in 1995 by William Roentgen. In the principle of operation of X-rays is the reverse of the photoelectric effect and can therefore be interpreted in a similar manner. So the photoelectric effect is just a reverse of the production of X-rays. The X-rays are produced when thermally generated electrons from a hot film. You can see it now. Filaments are accelerated through a high voltage and focused onto a tungsten target. You can see the tungsten target here. The electrons are produced by thermionic emission from the hot cathode. You can see the cathode there, the hot cathode. It's one that is going to cause the release of emission of the X-rays. So the electrons are produced by thermionic emission from the hot cathode, which is a heated tungsten filament. The filament lies inside a curved metal cylinder, which acts to focus the emitted electrons onto a tungsten target embedded in a copper block, which also acts as the anode. You can see the anode here. You can see the cathode arm. Tungsten, this is the tungsten, is used as a target because it is a metal of high melting point. The metal cylinder is kept at the high negative potential relative to the anode. This serves to accelerate the electrons through the X-ray tubes, which is also evacuated in order that the accelerated electrons can get to their target without losing much of their energy. A large fraction of the kinetic energy of the accelerated electron is transformed into heat when these electrons are suddenly stopped on hitting the tungsten target. So this is how electron is produced. The rest of the energy of the electrons is converted into X-rays, which are radiated from the tungsten target through a window. Radiated. You can see the X-ray beams that are produced here. The electric energy is converted into thermal energy of the thermionic electrons. This thermal energy is converted into kinetic energy of the accelerated electron. This is now converted into the electromagnetic energy of the X-rays. And this is the productions of X-rays. Types of X-rays: we have hand X-rays. And X-rays have a high penetrating power and a short wavelength. They can be produced by increasing the potential difference between the cathode and anode of the X-ray tube. Soft X-rays have a lower penetrating power and hard X-ray and longer wavelength. Hardness is a measure of the strength of the penetrating ability of the X-rays. Characteristics and properties of X-rays. Like light, X-rays travels in a straight line. They are not deflected by electric or magnetic field. They are diffracted by crystals. They cause fluorescence in zinc substance. They cause vibration of electrons when they fall on certain substances. They ionize gases. X-rays are used for examining the body to locate broken bones. They are used in airports to detect metals and contrabands in the baggage. In industry, they are used to detect cracks and flaws in metal cases, and they are used in analytical tools in investigating crystal structures and so on. They are used in treatment of tumors and some skin diseases. Cancer cells can be destroyed by X-rays. It can be used to detect alterations which have been made on work of art, and so on and so forth. And just like the radioactivity, X-rays to have effect, and you have to be careful. Exposure to X-rays can burn the skin, can also cause cancer. Deeper within the body, the X-rays can also destroy body cells. X-rays can cause genetic mutations. They can damage the body tissues. Special precautions are therefore necessary for people who work with X-rays. Wave particle paradox. Electron diffraction. The wave nature of X-rays was established by X-ray diffraction. In the Davidson and Gamma experiments, a beam of electrons emitted from a heated filament was made to impinge on a layer of a thin metal film or crystals. The electrons were diffracted and the diffraction ring were produced on a photographic Plate placed behind the thin metal film. Placed behind the thin metal film. Particle nature of matter or photoelectric effect. In the photoelectric effect, it was shown that when light falls on a metal surface, electrons are emitted from the surface. Similarly, when X-rays is allowed to fall on surface of a thin sheet also of metal like gold, the X-rays not only produce diffraction pattern but also acting like a particles. They may collide with the atoms of the metal and eject what? Electrons. The Compton effect. When a single X-ray photon collides with a free electron, the electron recoils as though it were a perfectly elastic sphere. In this effect, the scattered photon has a slightly lower frequency than the incident X-ray photon. In this phenomenon, matter in form of X-ray is shown to behave as a particle. Wave-particle duality. The wave-particle duality refers to the idea that light and matter such as electrons have both wave and particle properties. That is, light can either behave as a wave or as a particle, but not as both simultaneously. So some experiments, e.g. electron diffraction, indicates that matter behaves like a wave, but other phenomena such as the photoelectric effect and Compton effect experiments indicate that matter behaves like a stream of particles of photon. These two theories seem to be incompatible, but both have shown to have validity. Thus, it appears this is referred to as the wave particle duality or the wave particle paradox. The uncertainty principle. Einstein's uncertainty principle says that it is impossible to know accurately the exact position and momentum of a particle simultaneously. That it is impossible to know accurately the position and the momentum of a particle. You know, the momentum is mass times velocity. The uncertainty in the momentum multiplied by the uncertainty in the position approximately equals the Planck's constant. Because of the extremely small value of h, the Planck's constant, the uncertainty principle is of no consequence for objects above atomic size. And you see, this is all about our topic on the introduction to elementary modern physics. I hope you enjoyed the class. Thank you.